Power in research. What is a power analysis? A power analysis is a calculation that aids you in determining a minimum sample size for your study. Meaning of power. Power refers to the likelihood that a research will find a significant result, an effect, in a sample if such an effect exists in the population being studied. Cohen, 1998. The way a researcher poses the question about a significant result is through the use of null hypothesis. The null hypothesis always proposes the hypothesis that there is no difference between the experimental and control groups for the variable being tested. The null hypothesis is what all inferential statistics test. The statistical power of a study, sometimes called sensitivity, is how likely the study is to distinguish an actual effect from one of chance. It's the likelihood that the test is correctly rejecting the null hypothesis, i.e. proving your hypothesis. For example, a study that has an 80% power means that the study has an 80% chance of the test having significant results. A high statistical power means that the test results are likely valid. As the power increases, the probability of making a type 2 error decreases. A low statistical power means that the test results are questionable. Statistical power helps you to determine if your sample size is large enough. It is possible to perform a hypothesis test without calculating the statistical power. If your sample size is too small, your results may be inconclusive when they may have been conclusive if you had a large enough sample. Power. Jacob Cohen is the father of power analysis. Power is described as 1 minus beta. Acceptable power is 0.80 or higher. Some say that greater than 0.70 is adequate and greater than 0.90 is excellent. Power analysis is usually done a priori, but can also be done afterward. Controversial. Statistical power. The ability of a statistical test to detect a relationship or difference. The probability of rejecting a null hypothesis when it is false, and therefore should be rejected. Power range equals 0.0 to 1.0. Values cannot be interpreted directly. Calculate the probability of type 2 error, 1 minus power. The higher the power, the more likely to detect significant effect. The lower the power, the more unlikely to detect or find an effect, which leads the rejection of the null hypothesis even when there is real difference between the experimental and control groups. Power is the likelihood that a false null hypothesis, that is, there is an effect in the full population, will be rejected. Power therefore is a key factor to draw correct conclusions from the sample data. The table of types of errors shows the following headers: decision, null hypothesis is true and null hypothesis is false. Under decision, if the researcher accepts the null hypothesis, and this null hypothesis is true, the decision is correct. However, if the decision is false, the researcher commits type 2 error, an error due to power. On the other hand, if the researcher rejects the null hypothesis which is actually true, the researcher commits a type 1 error based on the alpha level or significance value. While rejection the null hypothesis which is actually false is a correct decision. As a researcher, one should control not to commit either type 1 or type 2 error in the course of making decisions. Another illustration about the truth of the type 1 and 2 errors. Assume that the null hypothesis is really true, that is no difference in the population. Following the arrows, if you do not reject this null hypothesis, then you commit a type 1 error. However, if you accept it, then you did a correct decision. On the other side, rejecting the null hypothesis means correct decision, while failure to reject this null hypothesis is a type 2 error. while the two boxes with arrows pointing to the decision of the researcher explains further the conclusiveness of the decision. Foundations of statistical power. Alpha level. Sample size, most dependent on this. Effect size. Type of statistical test being used. Type of design used. Alpha level, significance level. This is the p-value of the study set by scientific convention. For instance, the significance level of most social science studies should be 0.05 or less. Clinical studies require much lower than 0.05. Represents the likelihood of a type I error. It is the likelihood that the researcher will falsely claim a significant effect has been found when there is no effect in the population. Small sample that poorly represents the population has always a high probability that no effect will be found, or conversely, that any effect found in the sample does not exist the full population. To compensate a small sample size, the pilot study must use a p-value of 0.10 or even 0.20 in order to avoid abandoning what might otherwise be a promising line of research on the basis of a pilot study that finds no effect for the treatment. Sample size. The factor in statistical power most directly under the control of the researcher. The larger the sample, the greater the statistical power. The smaller the sample size, the weaker is the power. Effect size. Represents the size of the difference between the treated and untreated groups in a research study. Measures correlation. In t-test, this is the Point-Bese-Real correlation coefficient, ETA squared statistic for analysis of variance. Required in reporting the significance of the study. Although other sophisticated reader can estimate the effect size using the sample size and significance level, it is the responsibility of the researcher to provide the effect size. Effect size. Effect size emphasizes the size of the difference or relationship. For examples, the correlation between two variables, specifically r squared. R equals 0.1, weak, R equals 0.5, moderate, R equals 0.7, strong, R equals 0.9, very strong. The regression coefficient in a regression B sub 1, B sub 2, B sub 3. Relative to model and field. The mean difference in t-test, use Cohen's d. D equals 0.2. Small, D equals 0.5, medium, D equals 0.8, large. The mean difference in ANOVA, use ETA. 0.01, small, 0.06, medium, 0.14, large. If the effect size is small to medium, then the need of more subjects to find a significant result. If the effect size is large, then no need for additional subjects, even as little as 15 per group. The statistical test being used. Secondary factor that affects power. Each statistic has an associated power. Parametric statistics are inherently more powerful than non-parametric statistics when correctly used. Inappropriate use of parametric test puts the power into question. The research design, within subjects. Within subjects designs, repeated measures design, are the most powerful type of research design because each participant serves as their own control. Multiple observations of the outcome can be taken as well to understand longitudinal effects. There is always a drastic decrease in the needed sample size when using within subjects designs. Both large and small effect sizes are easier to detect when using within subjects designs. A within-subjects design is a type of study design that tests all levels of the independent variable on one group of participants. The goal is to observe all treatment conditions across each individual to compare the individuals to themselves and determine which treatment is the most effective. For example, in a candy taste test, the researcher would want every participant to taste and rate each type of candy. The research design, between subjects. When conducting between subjects designs, larger sample sizes are needed by default in order to compare independent groups. Larger sample sizes are also needed in between subjects comparisons to yield the most precise and accurate inferences related to differences between groups. A between subjects experimental design is a type of design where participants are split into two or more groups and each group is assigned a treatment condition. These treatments are then compared to the other groups to see differences in the outcome of the experiment. For example, if you wanted to determine if one type of cologne attracted more people than another type of cologne, you would use between subjects design. Regardless, between subjects designs will always decrease statistical power and increase the needed sample size. Other factors that affect power. Aside from the 5 components, other factors need to be taken into account when determining power. Variability. The variability of the population characteristics affects the power of your test. High population variance reduces power. In other words, using a population that takes on a large range of values for a variable will lower the sensitivity of your test, while using a population where the variable is relatively narrowly distributed will heighten the sensitivity of the test. Using a fairly specific population with defined demographic characteristics can lower the spread of the variable of interest and improve power. Example, minimizing variability. Stress is a variable that widely varies in the entire population of the Philippines. But the same variable can be more narrowly distributed, take on a smaller range of values, in a specific and well-defined population, like female college graduates under 25 years old. Low variability in stress levels will improve the power of the test in your study on stress. Measurement error. Measurement error is the difference between the true value and the observed or recorded value of something. Measurements can only be as precise as the instruments and researchers that measure them, so some error is almost always present. The higher the measurement error in a study, the lower the statistical power of a test. Measurement error can be random. Measurement error. Measurement error is the difference between the true value and the observed or recorded value of something. Measurements can only be as precise as the instruments and researchers that measure them, so some error is almost always present. The higher the measurement error in a study, the lower the statistical power of a test. Measurement error can be random or systematic. Random errors are unpredictable and unevenly alter measurements due to chance factors. Example, mood changes can influence survey responses, or having a bad day may lead to researchers misrecording observations. Systematic errors affect data in predictable ways from one measurement to the next. Example, an incorrectly calibrated device will consistently record inaccurate data, or problematic survey questions may lead to biased responses. How to increase power. Since many research aspects directly or indirectly influence power, there are various ways to improve power. While some of these can usually be implemented, others are costly or involve a trade-off with other important considerations. Increase the effect size. To increase the expected effect in an experiment, you could manipulate your independent variable more widely, example, spending 1 hour instead of 10 minutes in nature, to increase the effect on the dependent variable, stress level. This may not always be possible because there are limits to how much the outcomes in an experiment may vary. Increase sample size. Based on sample size calculations, you may have room to increase your sample size while still meaningfully improving power. But there is a point at which increasing your sample size may not yield high enough benefits. How to increase power. Increase the significance level. While this makes a test more sensitive to detecting true effects, it also increases the risk of making a type 1 error. Reduce measurement error. Increasing the precision and accuracy of your measurement devices and procedures reduces variability, improving reliability and power. Using multiple measures or methods, known as triangulation, can also help reduce systematic research bias. Use a one-tailed test instead of a two-tailed test. When using a t-test or z-tests, a one-tailed test has higher power. However, a one-tailed test should only be used when there's a strong reason to expect an effect in a specific direction. Example, one mean score will be higher than the other, because it won't be able to detect an effect in the other direction. In contrast, a two-tailed test is able to detect an effect in either direction. Thank you for watching. Please share this